Chapter 21, Alternating Current Circuits and Electromagnetic Waves. So, if you connect a battery to a circuit, that's a steady voltage, constant, called DC current, direct current. But, from AC generator, what we get is alternating current, right? It is not the same magnitude, changes magnitude. It even changes direction. It's like a sine wave, cosine sine wave. So this is more important because what the power we get from our household circuits, this is what the electricity board give us, is the AC, not DC. So we need to study AC circuits. So this is the contents of this chapter. So it's quite a large one, but however we omit a lot of them. Section 8 to 12 is omitted, so we only cover 1 to 7. We will cover up to this today, 1, 2, and 3. 4, 5, 6, 7 we will cover on Wednesday. So first topic is we have a AC source, our power source, not the battery, not the DC battery, but a AC source, which will provide a AC current. And we will connect it to a resistor and see how it behaves. Then we connect an AC source to a capacitor, only a capacitor, and see how it behaves. Then number 3, we will connect it to an inductor, the coil, and see how it behaves. Then number 4, topic number 4, we will connect all these 3. R is resistor, L is inductor, C is capacitor in series, so we call it RLC circuit, and connect it to an AC source and see how it behaves. Then we look at the power in an AC circuit. Number 6, resonance is a very important phenomena. In a series RLC circuit, we will have some phenomena called resonance, very important, and we will study that. Number 7, the transformers. Transformers are a device which convert one voltage to another voltage. That is called transformer. And we look at the principle of transformers. The rest of those things we will omit. Right. AC circuits power everyday electrical appliances, at your home, even here in the university, all these power sources, the power points you see there, what you get out from that is AC source, AC voltage and AC current, not steady current or steady voltage. AC means alternating. We have to look at various circuit elements. What are circuit elements? Resistor, R. The circuit element, the commonly occurring capacitor. The capacitance is C. Inductor, a coil. The inductance is L. So we will connect them to an AC source and see how they behave. Also, we look at what happens when these elements are placed in combination together. So we call it RLC circuit and see what happens. So first, some introduction to electromagnetic waves, very briefly. The light we receive from the sun is an electromagnetic wave. Light is an electromagnetic wave. What is electromagnetic wave? These are waves that consist of fluctuating, meaning changing electric and magnetic field. So the electromagnetic wave is nothing but the fluctuating electric and magnetic field. The sun emits electromagnetic wave, so we can see them only in the visible spectrum. It has got all kinds of energy. So we say the speed of an electromagnetic wave, C, the maximum speed anything can have is the speed of electromagnetic wave in vacuum. And it's equal to the frequency of the wave multiplied by the wavelength of the wave. So the value of C. Anyone know what the value of 3? It's roughly this, meters per second. So you can say 300 million meters per second. So you can write 300 into 10 to the power 6 meter per second. So 10 to the power 6 means million, right? So 300 million meters in a second. I hope I got it right. Yeah. So that is the fastest speed. Nothing can travel faster than that. So what we get from the sun rays is, electromagnetic waves of different frequencies. So it can reach from the zero frequency to all the way infinite, a whole spectrum. That's what we call a spectrum. What you can see with your eyes is visible light. We call it light. That's very small band in this spectrum. So you can give it in terms of either frequency or the wavelength. So when the frequency is small, mean energy is small, because it has that's how the frequency is related to the energy of the wave. So that mean when the wavelength is small, mean energy is the other way around. Wavelength is small, mean energy is big, because frequency and the wavelength multiplication is a constant. Big frequency mean small wavelength. Small frequency mean big wavelength. So here at the bottom, this is low energy mean long wavelength, 1000 meters. Say somewhere around here, the long wavelength, it can even be longer than that. So this way the energy is increasing and the wavelength is decreasing. So if you take the visible range of the spectrum, the electromagnetic wave, which you can see, it again we can break it into different colors. All they combine, it looks like white for us, but we can break it into colors. The bottom of the energy is the, what do you call, the red. The top is the blue and violet. So the bottom of the visible electromagnetic wave, visible light, is 700 nanometers. It probably corresponds to the frequency, I'm not quite sure. So here 10 to the power 15 in that range. You don't have to memorize this, but you should know roughly. Red corresponds to big wavelength, that means lower energy, and blue corresponds to higher energy. Okay. So, yeah. Blue, lower wavelength, high energy mean wavelength. So roughly, 700 nanometer, the wavelength nanometer, that will be red, and 400 nanometer, that will be blue or violet. So, if you go down, lower energy or higher wavelength, radio waves that you tune it to the radio station and all, that is in the range of meters, 1 meter, 2 meter, and so on. Microwave is smaller, higher energy compared to the radio wave, is centimeter range, and so on. And in the higher end, as the energy increases, you get above the blue, we have the ultraviolet, then X-rays and gamma rays, more higher energy, higher frequency. So you should roughly know the order. Okay, so right, now we'll go to the circuits. A circuit with a power source as an AC power source. An AC circuit consists of a combination of a circuit element. The circuit element can be a resistor, inductor, capacitor, and an AC source. It can be AC generator, that we saw that from an AC generator, what we get out is automatically alternating current source or AC source. And we saw the generate equation. It is a function of sine function of the time. So that means the EMF that we get out from those AC generator will be a varying sinusoidal waveform. Varies with time according to that equation. So we can get this, and we can say the potential difference that comes from an AC source at a time t, a maximum value, because here there is no time dependence, right? This is a constant. So the time dependence is only inside the sine. The maximum value sine can take is numerically 1. It cannot be anything greater than 1. That means the maximum value of the potential difference will be this part. And this is the maximum it can take is 1 only. It cannot be greater than 1. It can be anything from 1 to minus 1. So it can be even 0, okay, as the time changes. So here there are some other equation that comes in. This omega, which corresponds to the rotating velocity of the coil that is in the AC generator, we can give it in terms of the frequency of the sine wave. Frequency mean what? So you know the voltage changes with the time in this manner, cyclic. Yeah, the time that it takes to complete one cycle, if I call it the period, the frequency is 1 over period. That means how many cycles in 1 second. T, the capital T, is the time for one cycle. So 1 over T means how many cycles in 1 second. That's the frequency. So the frequency, the unit will be 1 over second, right? 1 over second. But 1 over second has a name. Hertz. Okay, so please remember this. Okay, 1 over second has a name. Hertz. So let me ask you a question. From our PowerPoint here at home and here in the university, it's an AC current. Do you know the frequency of that AC current? How fast it is? Hertz. Does it? How many hertz is our? No, that is the voltage. 60 hertz. Okay, 60 hertz. That means if the cycle happen, the time period of one cycle is 1 over 60 second. From here to here is just a fraction of a second, 1 over 60 second. So the frequency is 1 over 160. That means 60. 1 over period. Period is 1 over 60 second. So the frequency will be 1 over period. So 1 over 60 will be 60 hertz. So the frequency of this source is 60 hertz. In other countries like UK, the frequency is 50 hertz. Maybe when you buy appliances, you have to look at the frequency, because if you use a 50 hertz frequency in a 60 hertz source, it might have problems sometimes. Okay. There are some other equation we need to know is this one. This omega, we call it angular frequency because it is related to the frequency by this equation. It corresponds to the rotating velocity of the coil in an AC generator, but at the same time, it will be related to the frequency of the F through this equation. Omega is equal to 2 pi F, and in that mean the F is equal to omega over 2 pi. Okay, just rearranging that. Okay, so I hope that's clear. So let's move on. Let me ask one more question before that. The voltage that we get, we say it is 200 and what is the voltage that we get from our 220 or 10 or I don't know, 20, okay, 220 volt. Is that, what do you mean by 220? I told you it is AC. The voltage changes. Yeah. Now you are saying it is 220. You are contradicting, right? I mean, how can you say, what do you mean 220? Is it the maximum voltage 220? Maybe. Not really. It is an average value. So, because it is not always 220, it goes up, come to some value, maximum value, then go down, then it is repeating with time. So, this 220 is kind of an average value. So, it varies, right? Because 0, it even becomes 0. Then come to a maximum value, come down. This is not even the maximum value. It is some average value. We will discuss that later, how exactly we take the average value.
Why, if I put some machine at 110?
Yeah, because that machine is designed, suppose a machine is designed, appliance is designed for 110 volt. If you put it into this our 210 volt, it will burn, okay, because it will send big current and it will burn you become malfunctioning, okay. So you have to be careful. So that is designed for 110 volt. If you put it in 220 volt, it is going to get more current than expected value, it will burn. Other way around, may not nothing happen, but it will not work.
Yeah.
Suppose you have a 220-volt appliances and you go and use it in a 110-volt source, it may not work, but it will not burn because the current will be smaller. But if you take 110-volt designed appliances and put it in 210-volt, 220-volt, it will burn. Right, now let's move on. So now we will start the first topic. We take an AC source. So this is not like a battery. It's not a battery. What is the difference between these two sources? This gives you steady voltage, right? Say if it is 12 volt, it is always 12 volt. And this is the symbol for the AC source. It is not a steady volt. It is just changing up and down. So AC source. You connect an AC power source to a resistor. Simple circuit. We'll start with the resistor in an AC circuit. Now, the potential difference that comes from it, as you know, like in an AC generator, it will be a sine function. The time is in the sine function. So as the time changes, the voltage will change like this, the sinusoidal function. So it has a maximum value. So at any time, the delta V potential that comes out will be a function of the time. So t equal to 0, delta small v will be 0. As time changes, it's going to go up and down, even changes direction. Right, that is the potential difference. Now, what about the current through the circuit? Ohm's law. Ohm's law says the potential difference divided by the resistance will be the current. So we can use this together. Current, so we substitute for the delta V, divide by R. So you get this as the maximum current multiplied by the same sine function. So we see what's happening here is the potential difference and the current both have the same kind of sinusoidal relationship. So when the current is 0, when the potential difference is 0, current will also be 0. When the potential difference is maximum, current will also be maximum. So let's look at the graph. So this is the graph that shows both the potential difference and the current as a function of time. The maroon line, okay, this is the maroon line. At t equal to 0, potential difference is 0. And the potential difference increases and come to maximum. What about the current? Current, of course, will behave in a similar manner. When the potential difference is 0, current is also 0. And when it is maximum, current is also maximum. They are in step. We say it is in phase. So I can understand what I'm saying here. Both the current and the voltage follow the same pattern. Okay, of course, one is current, other one is potential difference, two different things, but they step together. So we say in phase. Now, you have to remember this word. I hope you understand the meaning of in phase. The current and they move together. They both have the same function. So, okay, together, step together, like two people, soldiers marching, right? They are in phase. So when one soldier put the other soldier also put the left foot forward. They are in phase. They are walking together. They are marching together. So it is in phase. So this is very important, okay? In a simple AC circuit with only the resistor, the potential difference across the resistor and the current through the resistor are in phase. Voltage and the current go together. Maximum, both of them are maximum. When both of them are 0, together. And both of them change the direction together. So on. So look at this graph. They are in phase. So very important that you understand this concept. The current and the voltage reach their maximum value at the same time, go to the 0 at the same time, and so on. Though we say the current and the voltage are in phase. Note this word. Okay. Now, about the power. Power mean what? How much energy is used up in a given time, energy per second, how the energy is used, consumed in the resistor, rate, at what rate it is consumed in the resistor. It doesn't matter whether the current is flowing to the right or to the left. Does it matter? No, because I squared, right? The power is I delta V. So I want the power inside the resistor. You can write delta V is equal to IR. So you get this expression, the instantaneous power through the resistor is I squared, the instantaneous current. The current is changing. So at any given time, the power will also change because I is different at each moment in time. So it doesn't really matter. The power is the same if the magnitude of the current is same, whether it is going to the right or to the left. You don't care. It is I squared anyway. Even if you put a negative value for I, plus 10 squared or minus 10 squared, it is the same power. So it doesn't really matter the direction of the current. The heating effect produced by an AC current with a maximum value of I max is not the same as that of a DC current of the same value. Now, let me explain what we are saying here. Let's say you have a resistor and you say the current, this is a DC source. So the current is always 10 amperes, right? Always 10 amperes. So the power that is dissipated here will be 10 squared multiplied by the resistance. Let's say we put a AC source. And let's say the maximum current is 10 amperes. AC source means it is always not 10 amperes. Only the maximum current is 10 amperes. Do you think the power here and here will be the same? No, because this is always 10 amperes. It is only time to time 10 amperes for short time. So the power dissipated here will be less. Okay? Because, why? Less, because I'm saying this is the maximum. So all other time it is less than 10 amperes. Only, once in a cycle, 2 times in a cycle, it will be 10 amperes. Other times it will be less than 10 amperes. So that's what this is saying. The heating effect produced by, the heating effect is the power, right? Heating effect produced by an AC current with a maximum value of I max is not the same as that of a DC current of the same value. Because the maximum current occurs for a short while, so moment only, 2 times in a cycle. So this equation is the instantaneous power, because the I here is the current at a one given moment. So we need to know the average power in an AC circuit. Because the power is not always the same, we need to be able to calculate the average power. How can I do that? In order to do that, I need to introduce the concept of RMS. RMS value is the average value when you have a sinusoidal variation, average value. So let me start with the RMS current. Can I get an average value for the current in an AC circuit? How we do that as follows. Could you please pay attention? Look, this is one cycle. If someone asks you what is the average current, what will be your reply? How do you take average? If you have two values, 2 and 5, how do you take the average of this 2 and 5? Divide by the number of times, right? So you have only two values. 2 plus 5 is 7. Divide by 2. Let's say 2, 3, 5. You add the three numbers and divide by 3. Okay. Now, in this cycle, if someone asks you find the average current, what is your quick reply? Yeah, but there are so many. How many values we have? Infinite number of values. What is the average current here? You have an answer, very quick answer. For every plus 5, you have a minus 5. So average is 5 plus minus 5 is 0. 6 plus minus 6 is? So that means in a cycle for AC, if someone asks you what is the average, the answer is 0. For every positive value, there is a negative value. So in an average current, if you ask, it is 0. Obviously, it is 0. But for power, does it matter whether the current is flowing right or flowing left? Doesn't matter. So average power is not 0. Obviously, it is not 0. So this is why we need to get a special average value. What we do, we square the current. What is this S stand for? Square. S is for RMS. S mean square. M mean no, mean. You know what is mean? In statistic math? Average. Mean average. So S for square, M mean average. So take the squares of the value and take the average of the square, and what is R? Root. Root means take the square root. So you take the square of the values, I1 square, I2 squared, and take the average of these I1 squared plus I2 squared. After doing that, take the square root of that average value. So that's why it is called root mean square. So this is the trick. If you just take the average, what happened? It is 0. That, obviously average power is not 0. Average power depends on the I squared, not on I. So this is what you do. In order to get an RMS value, the proper RMS value, take the average of the squares, then take the square root. So that's how you take the average value. And it can be shown, we'll prove it in the next slide, such RMS value is equal to the maximum value divided by square root of 2. Because sinusoidal mean, it has maximum like that, right? Take the maximum value and divide it by the square root of 2, that will be the RMS value. So this is the correct representation for an average value for IS. Square 2 is a constant, yeah, square root constant. Yeah, in fact, if you use a calculator, 1 over square root 2 is equal to approximately, to 3 significant figures, it is 0.707. You should have come in the beginning of the class. You cannot come right now. It is 30 minutes past. Come and sit here, please. Okay, so this is the idea of the RMS value. So this is the proof why RMS value is maximum value divided by square root 2. This is where we are proving it. Let's see. So this is current versus time. So you know the current is changing in a sinusoidal manner. It's a sine function or cosine function. Now I take this and square it. I squared versus time. So what happened in the positive half of the cycle? It will be like this. The 0 will be 0, and I maximum value, when you square it, it will be going up. Now in this part, when it is negative, it will be the same, right? Because the negative value, when you square it, again it will be flipped up. It will be positive. So this is I squared versus time, and it is easy to get the average of this. Now nothing is negative now, everything is positive. It can be shown very easily from the sine function. I will not bother you with too much. The average will be simply, average of this will be simply half of the maximum value. Yeah, it can be proved using the sine function or cosine function. So the average of this will be simply half of the maximum value. So now you are proving that I squared average is equal to half I maximum square. Okay. I mean, I didn't strictly showing it, not rigorously, But just take my word for it. It is easy to show you from for cosine function. So it is true. Now, what is the definition of RMS? RMS is take the square root of this. That is the meaning of RMS. Take the average of the squares and take the square root. So it is 1 over square root 2. Square root of this will be I max. So we have proved it. RMS value is simply maximum value divided by square root of 2. So it is for the current. We can similarly, it is valid even for the voltage. So delta V RMS is equal to delta V max divided by square root 2. Okay. So I showed it for the current, and it is the same thing for, because they are related simply by the Ohm's law. It's just a factor. V is equal to I into R is a constant, so it is valid for the delta V as well. Now we are going back to the power. So instantaneous power at any time is the instantaneous current squared into R. So the average power will be, in place of the I, we put the average value, which is IRMS squared into R. So this is the average power, will be simply the average current, which is our RMS current squared multiplied by R. Now we have some notations, rules. Whenever we are referring to the instantaneous value for the voltage and the current, we use small letter. So potential will be small v, delta small v, and for the current, small I. For the maximum value and the RMS value, you use the big letter, the capital letter. Okay, this is the notation. So you should understand, whenever you see small letter, it is referring to the instantaneous value. When you use for the constant values, the maximum and the RMS value, you use the capital letter. RMS value will be used when discussing AC currents and voltage. Yeah, now I go back to my original question. Now I said, when someone asks you what is the voltage you are getting from your power point at home or here, you said it's 220 volt. Is it it's an average value, right? Is it the RMS or the maximum? Is the RMS, okay. So what about the maximum then? So in your AC source, you are getting the time versus voltage. It's an average value, right? 220 is the average value somewhere here. So what is the peak value? Maximum value will be delta V max. According to the definition, it will be square root 2 multiplied by 220. So can someone calculate it for me? 220 multiplied by square root of 2. Somebody told me 296. Somebody check that, please. Multiply by square root of 2, because RMS is maximum divided by square root of 2. Excuse me, where are you going? You're not supposed to, you come. I'm not going to take you as present. You put it out, please turn it off. You not only come late, and you are going to leave the class, and you want me to take attendance? 296? No. 311, I don't know. Okay, are you sure? All right, 311. I don't know, I didn't check. Somebody told me in the last class, okay? Right, anyway, my point is, so this 220 volt is an average value. So actually, the voltage is varying between 0 and 311. So it 0, then goes to 311, come down, reverses direction, and so on. So it's a sinusoidal waveform. Right, so we can write the Ohm's law in terms of this average value. So we will say the potential difference across the resistor, its RMS value is equal to the RMS value of the current multiplied by the resistance. V is equal to IR, the Ohm's law. So you can also write it in terms of the maximum value. In that case, both side maximum. So potential difference across the resistor, the maximum value is equal to the maximum current value through the resistor multiplied by R. So that is the Ohm's law applied to AC circuit when you have a resistor in the circuit. So that we've done with a simple circuit of AC source and a resistor. Now, next one is capacitor. So we take an AC source and we have a capacitor. So this is our simple circuit again. Now things are going to get interesting. Resistor is, as expected, nothing unexpected. But here things are going to get a little bit interesting. Let's say the potential difference is, of course, given as a sine function. So this is our source. Delta V is the maximum value, but it is going to change because of the time dependence inside the sine. Remember, when you had a battery, a DC source, and a switch and a capacitor, when you close the switch, what happens? The potential difference across the capacitor is, does it become? No. How do you get the potential? The charge build up here, right? What is the charge initially? Because Q is equal to C delta V. Initially, the charge is 0. That the potential difference will be 0, right? At the beginning, as you close the switch, it doesn't become, say this is E, EMF of the battery is E. Does it immediately become same as the battery? No. It builds up slowly. The potential will be 0. Then as the charge accumulate on the plates, the potential will increase, and at the end, it will become the same potential as the battery, but in the opposite direction. There will be no more current flow. But what about the current? Current, the moment you close the switch, there will be a big current, and it comes down. See what's happening here? They are not in phase. When the potential is 0, current is already maximum. And when the potential is maximum, current is 0. So there is out of step. They are not in step. In the case of the resistor, the potential difference across the resistor and the current through the resistor in phase. Now they are out of phase. So let's look at the, okay, now I have to read this. Current starts out a large value, but the potential difference will be 0. There is initially no resistance to hinder the capacitor. At the beginning, like no resistance, the current will be maximum. But as the charges build up between the plates, the current will decrease, okay, because it's getting the same, there's a potential difference from the capacitor plates in the opposite direction, so it will start reducing the current. And when the plates are fully charged, potential will be maximum and the current will be 0. So if you look at the graph, this is what we see. The maroon color is the voltage. So voltage is 0, but the current is maximum. When the voltage is maximum, the current is 0. So they are out of phase, not in phase, they are out of phase. And you can also give how much it is out of phase. Look at this. This is one cycle, right? This is one cycle. The cycle repeats again and again. This one cycle is one period. We can say it is one complete cycle, corresponds to 360 degrees in angle. One cycle corresponds to 360 degrees. And you can see that this one cycle can be divided into 4 parts. When it comes to the maximum, that is quarter of a cycle. Again, go to 0, another quarter, half the cycle. Another quarter, 3/4 of the cycle, that's come to minimum, or the maximum in the other side. Then you go back to the original starting point. So the whole thing repeats. So we can divide it into quarter parts. What is quarter of 360 degrees? 90. 360 divided by 4 is 90. So if now I can put some number into how much is the difference in the phase between the current and the voltage. You can see the voltage or the current is ahead of the voltage by 90 degrees. Or you look at in the point of view of the voltage. The voltage is 90 degrees current. So we say the voltage across the capacitor lags. Note this word, lag. You know what is the meaning of lag? Behind. What is the opposite of lag? Lead. Leading, leader, leading. So voltage lags the current by 90 degrees, quarter of the cycle. So we have to remember this, okay? These are not in the formula sheet. So when you have a capacitor in a circuit, in an AC circuit, the voltage across the capacitor is behind the current by 90 degrees. They are not in phase, they are out of phase by 90 degrees. The voltage across the capacitor lags behind the current by 90. There are some animation which I forgot to show you. Maybe let me show it here. So here, this is our resistor. Okay, this is our resistor. This is the only resistor of the capacitor, and we have the AC source here. This is a meter to measure the current, the red one, and the blue one is the meter to measure the voltage. Now you can see that when the red one is the current and the blue one is the voltage. So when I start, you can see they are in phase, right? The dot shows the time. At that time, the projection of the see this. Let me pause at one point. Okay, I have paused it. Now let me explain that. So the red one is the, what is the red one? Red one is the current. Okay, red one is the current. So the projection of the current on the y-axis, this is the instantaneous current at any given moment. So we call this arrow as the phasor. We'll come back to this again later. So we can represent the instantaneous current at any given time by this arrow. So the projection of the arrow onto the y-axis will be the instantaneous value of that phasor. So here, the current is this much. And what about the voltage? Voltage will be, so it's better I choose the color correctly. So let me use the red for the current. Red is for current, yes. So the projection of this into the y-axis, because the sine theta, is give you the current at that particular time. So where is this guy? Here. Okay. Now, what about the voltage? Voltage is by the blue arrow. So the projection of that into the y-axis give you the voltage at that particular time. So this arrow representation is called the phasor. So we'll come to this again later. So just please remember that. So now you can see they are going together, right? These two dots is moving together when I start the animation. So they are in phase. So now let me make this capacitor. So let me clear this marking. So I put this one is an our capacitor. Oops, I didn't come. Reset capacitor. Okay, now it is a capacitor. Now see what happened. They are out of phase. So let me run that again. They are out of phase. So the you can see the phase, so how it behaves. The blue arrow is the voltage, and the red one is the current. The blue is behind the current just exactly by 90 degrees. So the voltage lags the current by 90 degrees when you have a capacitor. pause and come back to this. Right. Now, in this circuit of AC source and the capacitor, like the resistor, when we have a more voltage, the current will be more. When you have a smaller voltage, the current will be smaller. But there is a lag between them. So we can call this impeding of the capacitor on the current in an AC circuit as a reactance. We don't say resistance. Resistance is the term reserved for resistors. So the effect of the capacitor on the current through the circuit is called the reactance. Okay, so you should not say it is resistance, we call it reactance. So we will have a similar thing with the inductor also. So there's a reactance from the capacitor, also there's a reactance from inductor. So because it is from the capacitor, we call it capacitive reactance. Okay. So the capacitive reactance is given by, we use the symbol X for reactance. And because it is from the capacitor, we put the subscript C. So capacitive reactance is X sub C. And without showing how it is so, I will just give the formula. The capacitive reactance depends on the capacitance. Also, it depends on the frequency of the AC source. So when the frequency increases, the reactance or capacitive reactance will decrease. When the capacitance increase, it's an inverse relationship between the reactance and these F and C. F is in hertz, that means per second, and capacitors in farad. One can show second farad per second is the same as ohms. Okay, I'll not go into the detail. It can be shown. You don't have to worry about showing it. Just take my word for it. Farad second will be exactly equivalent to the unit ohms. So it has the same unit as resistance, but it's not resistance. This is called reactance. So then the Ohm's law for a capacitor in AC circuit. So potential difference across the capacitor RMS value is equal to current RMS value multiplied by not resistance but reactance, capacitive reactance. Delta V is equal to I into R, but R is replaced by its reactance, not resistance. So you need to know these formulas. Of course, it will be in the formula sheet. Okay, all you have to do is to look at the formula. Even if you forget, no problem. You should know the Ohm's law. Delta V is equal to I into R, but instead of R, you put the reactance. Wait for a capacitor, capacitive reactance. So we can now even solve a question. We have a simple AC circuit, so AC source. It is connected to a capacitor. Let's say there's a switch, okay. So the capacitance is given 18.7. The frequency of the source is given 85 hertz. And the RMS value of the potential difference is given of the AC source, 192 volt. Question. So what is the current through this circuit? When you close the switch, there will be a current flowing, the RMS value of the current. So simple, you just use Ohm's law. Current is equal to potential difference divided by not resistance, because we don't have a resistance, we have a reactance, capacitive reactance. So instead of resistance, you put the reactance. The symbol for reactance is X, but it is for capacitor, so X sub C. Right, now, do you know is it given here in the question? Is the reactance given? No. Is this given? Yes. But this is not given. But we have to know there is another equation, which is this. Reactance is in terms of the frequency of the source and this is given, this is given. So we can calculate the reactance. So, we can just put it like this, divide by this. That means it become like this. This is given, this is given, this is known, this is given, this is given. Substitute, you get the answer. Done. Okay. Right. Now we go to the third topic. So we are one by one, right? We started with the resistor. We saw in a resistor, the voltage, the potential difference, and the current are in step, in phase. In a capacitor, the potential difference and they are out of step. By how much? Voltage lags the current by 90 degrees. And then, we got the Ohm's law and we even did a question. Now we go to the third topic, inductors in an AC circuit. So we have an AC source. Instead of the capacitor, we put an inductor. And what happens now? Let me go back to the DC case. Suppose you have a battery like this and a switch. Do you know what happens now? When you close the switch, what happened? Faraday's law. There's supposed to be a current, but this guy, there'll be a magnetic field, that's a flux change. He doesn't like it. This will immediately, at t equal to 0, it will act like a battery with the same EMF as this, but in the opposite direction. So it will make the current to be 0. When you close the switch, current will be 0. Well, what is the potential difference? Current is 0, but the potential difference across the inductance is maximum. Same as the battery voltage. Now see what happened. Who is ahead now? The voltage is ahead. When you close the switch, immediately there will be a potential difference. Excuse me, please come to the front. Yes. Anytime, every time I look at you, you are talking. The potential difference is leading. It is the same story. When the potential is maximum, current is 0 because start with the 0 current. And then eventually this potential will be 0 and the current will be maximum. So when you have an AC source, it will repeat. So you will have this graph. The maroon line is for the potential. So if you take this particular instance, at this t equal to 0, you have the potential maximum, the current is 0. So when the current potential comes to 0, the current will be maximum. So and so on. The same story will repeat every cycle. So what you have to take from this graph is the voltage leads. Voltage is the first guy, right? Because when you look at the DC case, the moment you close the switch, voltage is already the same as the battery. So the voltage is in front of the current. Voltage is maximum, current is just starting to from the 0. So voltage leads the current by 90 degrees. We can look at the animation, but I leave it to you. I don't have to repeat it. Okay, so now go to the Ohm's law in the case of inductor. So this time we have a reactance like in the case of the capacitance, and we call it inductive reactance. The symbol is X with the sub L. So the inductive reactance is again function of the frequency and the inductance of the inductor. But we have to compare this what we had for the capacitor. See, inductive capacitance is inversely proportional to the frequency and to the capacitance, but inductive reactance is directly proportional to the frequency and the inductance. So please take a mental note of that. So the way it depends on its frequency and its inductor or capacitance is here it is inversely, there it is directly proportional. In the same way like we did before, if you take the unit, this will be per second, this will be Henry. One can show Henry into per second is the same as ohms. Now, I talked about this is 1 over, right? Yeah, 1 over per second farad is ohms, not second per farad, because the whole thing is underneath. So 1 over second inverse farad is equal to ohm. So here it is second inverse Henry is equal to ohm. So inductive reactance also has the unit ohms. So then the Ohm's law will be like delta V is equal to I into, instead of resistance, we have the reactance. Here it is the inductive reactance. Right, so in this chapter, we looked at resistor with the AC source, then inductor only with the AC source, then a capacitor only with the AC source. Now we put them all together. So we call it RLC. They are connected in series. So RLC series circuit. And you want to know what happens now. Previously, we knew that only resistor, the current and the voltage will be in step, in phase. Only inductor, the voltage will be ahead of the current by 90 degrees. Only capacitor, the voltage will be behind the current by 90 degrees. So this is, we put them separately. Now we are going to put them all in series. Now let's say, okay, all these things will going to affect differently. R will be in phase, this will be out of phase, 90 degrees, plus 90, minus 90. What happens if you put them all together? Let's say the current is given by this, okay, so current when t equal to 0, current will be 0, then it will go up and down in the sinusoidal. The current is the same through all of these elements, and the voltage from the source, if I call delta V, will not be the same t equal to 0, it will not be 0, it will be, there will be a phase difference. Now you cannot say it is 0 or plus 90 or minus 90, it is going to be something in between, some other angle. Yeah.
The delta is positive 90, right?
If only inductor, if only inductor, the current and voltage will, there will be a phase difference of 90 plus 90 degree if it is ahead. Capacitor will be minus 90, the voltage will be behind the current. If resistor, no change, they will be together. Now what happens if we put them all together in a series connector like that? So that's what we are going to investigate. Right, so let us look at this graph. This graph A, picture A, is the current versus time. T equal to 0, the current is 0, it's going up and down like that. If you look at the voltage across the resistor, it will be in step. Only the voltage, it will be like the current, resistor. There is no phase difference, there is no out of phase, it will be in phase. Only the potential difference across the resistor. Potential across difference of the voltage across the inductor, it will be ahead. When current is 0, the voltage is already maximum. It is ahead, 90 degrees plus 90 degrees. The potential across the capacitor will be behind. Okay, when it is maximum, it will still be 0. So it is 90 degrees behind. So these three are the voltages across each of these separately. Like if we go back here, so this across the resistor, this is across the inductor, this is across the capacitor. The total voltage is the sum of these, right? Sum of these. But the instantaneous value of the voltage, the total voltage will be the sum of these three voltages here. So what I will do now, I will add them to get the total voltage. So it will be, it will be starting somewhere here, it will be out of phase with the current. By how much, we don't know. It is not 90, not minus 90, not 0. It can be any value between 0 and minus 90 and plus 90. So to figure this out, we use a technique called phasor diagram. So we saw with the animation, if you remember. So what we do here, the current, its maximum value, we represent by an arrow, say this is the current, t equal to 0, okay, the I is equal to I maximum sine 2 pi f t. So t equal to 0 current, at t equal to 0, if you represent it by the maximum value by this arrow, we call that phasor. This rotating vector, as the time changes, it is going to go around like that. Okay, at t equal to another time, it will come somewhere here and it will go around. So at t equal to 0, the phasor for the current is along the x-axis. So it has the projection of that on the y-axis 0. The instantaneous current is 0, but it has this maximum arrow that represented by this arrow, the maximum value of it. So as the time changes, it's going to rotate. And then we look at the voltage. We know now the total voltage, the sum of all the three voltage, let's say we represent it by this arrow. It will not be in phase with the current. It will have certain angle phi, something in between minus 90 and plus 90. It could be 0 or other than 0, any value. We don't know what it is. Let's say it is some value phi. So the projection of that into the y-axis will give you the instantaneous value of that voltage. So we call this diagram as phasor diagram. This rotating vector is called the phasor. So you should remember these words. Okay, we represented by an arrow, the maximum length of that, and it just rotates. The projection of that on the y-axis will be the instantaneous value of those voltages. And the angle phi, the difference between the voltage and the current, is called the phase angle. Phase angle. So we need to know this terminology. Right. Now, in order to get an expression for the total voltage maximum value, can I say it is equal to the maximum value of the voltage across the resistor plus the maximum value of the voltage across the capacitor plus the maximum value of the voltage across the inductor? No, it's not true, because they are at different. So the phasor is pointing at different angle. There are a phase difference between them. So we have to add them like vectors. So you know that if the current is along the x-axis when time t equal to 0, the potential or the voltage across the resistor will be in phase, in the same. But the potential or the voltage across the inductor will be 90 degrees ahead. And the potential across the voltage, rather let me call it, voltage across the capacitor will be 90 degrees behind. So I can see that the phasor for inductor and the capacitor voltage will be in the y-axis. Now we can add like we add vectors to get the maximum value of the total voltage. So you know how to add vectors. What is in the y-axis is easy. So both of them are in the y-axis. So if you want to add delta VL and delta VC, I can say this addition will be simply, let me use another color, say red, maybe blue. So it will be this arrow, which will be delta VL minus delta VC. So I added these two. because this is the positive y-axis and this is the negative y-axis. So we can just simply add them like that. Then we have this one and that one. One is along the x-axis and one is along the y-axis. So you can draw this parallelogram, and using the Pythagoras theorem, you can say the total potential delta V max equal to x component, if I call it component, delta VR squared plus y, which is delta VL minus delta VC. So that is the y component delta VL minus delta VC, the whole thing squared, take the square root of that. So it's like treating them like vectors, one along the y-axis, the other one is along the x-axis. And you can also find the face angle by the definition of tan of this angle will be equal to adjacent, which is delta V, no, opposite, right? What is tan? Opposite side divided by adjacent. Opposite side is delta VL minus delta VC divided by delta VR. So that's what you're going to get here. So I took it out. So you see this is already done for the VL and VC, and this is the VR. Now I want to add them. So this is equal to square root of delta V R squared plus delta VL minus delta VC, whole thing squared, add the two squares things, and then take the square root, you will get the magnitude of the total voltage, and the angle phi will be from the tan phi. Here it is, and this is the angle. So let me tell you why we do have to do this. These voltages are not in phase. So they cannot simply be added. You cannot say the total voltage is equal to delta VR plus delta VL plus delta VC. Delta VL and VC, luckily we can do this. One is along the positive y-axis, the other one is along the negative y-axis. And this is the x-axis, so we have to do this way to get the total voltage, its magnitude. Right. So the angle phi will be tan inverse, the ratio of the y component divided by the x component. Now we got this for the maximum value. We can do it for the RMS value as well. So all you have to do is instead of max, you put RMS everywhere. So the relationship between RMS and maximum is the factor of square root of 2. So if it applies for maximum, it will also apply for the RMS value. Now we are ready to do an example question. We have a resistor, inductor, and a capacitor connected in series with the voltages across the resistor in the same order. This is the delta VR, and this is the delta VL, and this is the delta V capacitor. Please come to the front. Stand up, come to the front, please. Excuse me, come to the front. The question is, find the total voltage, the maximum value, RMS value. These are all RMS value. You already, I hope you remember the equation. It is what is in the x-axis is only the, excuse me, come to the front. And what is in the x-axis is, y-axis is this. Square them and sum them, take the square root. All you have to do is just substitute the values. So delta V of R is 78 square it, and 133 minus 69, square it, take the square root, you will get the answer. B, second question, what is the magnitude of the phase angle? Phase angle is tan phi is the ratio of the y component, so that will be delta V L minus delta V. C divided by the x, the horizontal axis is the delta VR. Again, you substitute the value and get the final answer. So it will be 133 minus 69, no, 133 minus 69 divided by 78. Okay, so I'm not going to, please come to the front. Sit. Now we talk about the resistance and reactance. So resistance, we can say it is in the along the x-axis. Okay, it is in the same phase as the current. So we put it in the horizontal or the x-axis, and the capacitors and inductors, they also, like the resistance, it will reduce the current, but at the same time it will also shift the phase. It will not be in, please put your phones away. Excuse me, put your phones away. It will be in the perpendicular to the direction of the current, the resistance. So in a similar manner, I can say the total resistance, we call it the impedance. So we got the resistor and the inductor and the capacitor connected in series like this. So if someone asks what is the total resistance due to all these three, we give it the name impedance because that consists of resistance, as we call it, coming from the resistor, and the resistance which we call the reactances coming from the inductor and the capacitor. We have to add them, but it will not be simple addition. You cannot say Z is equal to, just because they are connected in series. If you say it is equal to R plus XC plus XL, that is wrong. It will not add like that because they are perpendicular to each other. So in the same way that we did for the voltages, we say the reactances are in the y-axis, L is in the positive axis, and C is in the negative axis. Therefore, the Z is equal to square of the X plus the square of the Y. Add them and take the square root. That will give you the total resistance. This is actually combination of resistance and reactance, and it has a name. We say impedance. We don't call it resistance. We don't call it reactance. It's a combination of both. The name for that is impedance. And the symbol we use for impedance is the letter Z. So impedance, we get like this. And this phi is the same, the angle between the total voltage and the current. So therefore, I can also say that the phase angle is equal to, in terms of the reactance and the resistance, in this manner it is equal to the reactance, the total reactance divided by the resistance. Before we had the other equation, they are both correct. Okay, this is also correct. That is in terms of the voltages. Both of them give the angle phi. Okay, now we can do the Ohm's law for this RLC circuit. Ohm's law is what? Delta V is equal to current into the resistance. But here, instead of just simple resistance, we have got the impedance. So we replace the R by Z. So again, we can give it in terms of the RMS value or in terms of maximum value. Both are correct. It's a factor of square root 2 between them. So we can regard this as the generalized forms of Ohm's law applied to a series AC circuit. Summarizing what we learned so far, we can put them all together. So if you only have a resistor, the impedance will be just R, the resistance value, and the phase angle will be 0. Okay, so when you only have a resistor, the current and voltage are in phase, so the phase angle is 0. When we only have only a capacitor, the impedance will be just the capacitive reactance, and the voltage is behind the current by 90 degrees. When we have only a inductor in the circuit, like something like this, then the impedance will be just the inductive reactance, and voltage will be ahead of the current by 90 degrees. Then we can have a combination like this. We may have a resistance and a capacitor, no inductor. So that will make the impedance to be this, because there is no XL. And this time we have only a capacitor. That means the phase angle is going to be positive. Voltage is behind, negative. Phase angle is going to be negative, but not negative 90. Negative 90 if there is no resistor, but we have got both a resistor and a capacitor. So it will be pushed toward the positive, a little bit less negative. So it will be something between minus 90 and 0. Since there is a resistor, it will be less than minus 90, but more than 0. Well, not 0, between minus 90 and 0. Then we can take this case of no capacitor. That means the phase angle will be positive because there's no capacitor to make it negative. What happens with the inductor? It will push towards the 90 degrees. If it is pure inductor, it will be exactly 90 degrees. But we also got a resistor, so it will be something between 0 and 90. This is the general case when you have all those three. So the impedance will be this. And here what happens, we have to look at this. If XL, the reactance from the inductor, is greater than the reactance from the capacitor, it will be positive. If the other way around, if the reactance from the inductor is less than the reactance from the capacitor, it will be negative. Problem solving techniques for RLC circuit, you may have to calculate the reactances, which we call the XL and XA. Do you remember the formulas? It's a function of the frequency, and in the case of inductor, it is a function of the inductance. The capacitive reactance is this. Of course, this will be given in the formula sheet, but no harm memorizing it. So you will use this formula to calculate the XL and XC, and the R, maybe it is given, and then from that you may have to find the impedance, the total resistance and reactance. Then probably you have to find the current, the maximum current or the RMS current. Then you will be applying the Ohm's law. So suppose we have current is known and the impedance is known, then you can calculate the voltages. So the question may vary. Sometimes voltage impedance will be given, ask you to find the current. So it depends on the question. Maybe you may be asked to find the phase angle as well from the given data. Right, now we come to power in an AC circuit. If you have a pure capacitor or pure inductor, there will be no power losses. Okay, there will be, because we assume pure mean ideal capacitor, ideal inductor, there's no heat losses. If it's an inductor, the coil has no resistance, so there'll be no power losses. Guys, please come to the front, put your phones away. Come to the front, please. So what happened in a pure capacitor? During one half of the cycle, energy is stored in the capacitor. Okay, so it is connected to a AC source. So you know the current changes, the value changes. So one half of the energy is stored in the capacitor. Other half the energy is returned to the circuit as the charge is lost in the capacitor. Okay, then it give back to the circuit. Similarly, in a pure inductor, one half of the cycle, the energy will be stored in the inductor because the source has to do work against the back EMF of the inductor. So it will be stored in the inductor in the form of magnetic field. So when the current begins to decrease, the energy will be given back to the circuit. Right. Power that delivered to the resistor will become the internal energy in the resistor. So you can say the average power will be the RMS current through the resistor squared multiplied by the resistance. So that is coming from the definition of the power. Now I can write this square as two terms. Instead of saying I square, I will write I into I. So we can do that, right? Now why did I do that? If you look at this part, this is the potential drop. This is the potential drop across the resistor. So I will write for this as the voltage across the resistor. So this equation now become the current through the circuit multiplied by the voltage across the resistor. So the current through the circuit will be the current through the resistor. So the current through the resistor multiplied by the potential the voltage across the resistor. Now I draw the phasor diagram again. So this is the potential or the voltage across the resistor. This is the difference between the potential across the inductor minus the potential across the capacitor. That means what that is in the y-axis. So this is the total potential. Now if you look at this right angle triangle, you can see that you can write this as, this is the adjacent for this angle phi, as delta V RMS multiplied by cosine phi. That is the definition of cosine. Cosine is what? Adjacent divided by the hypotenuse. So adjacent will be equal to hypotenuse multiplied by cosine phi. So for this, I can write in terms of the total voltage. So this is the voltage across the resistor. I can say it is the voltage, the total voltage multiplied by the cosine of the phase angle. So finally, we get this expression for the power, IRMS, that the current through the circuit, multiplied by the source voltage, which is the total voltage, multiplied by this factor cosine phi. So we call this cosine phi as the power factor of the circuit, power factor of the circuit. Yeah.
Will it always be a right angle triangle?
Yeah, because what we are doing here is putting the voltage across the resistor, which is along the, if you take a horizontal axis, the voltage across the capacitor and inductor is in the vertical axis. So, of course, they are at right angle.
We can use sine, cosine, and
Yeah, yeah, yeah. Cosine phi is have the name power factor. You need to know these notations, right? The names, power factor of the circuit. So we can see that if we want maximum power, we have to make the cosine phi to be maximum. What is the maximum value cosine phi can take? Cosine is 1, right? Cannot be more than 1. So when cosine phi become 1, for what value of phi? 0. So phi equal to 0 mean the total potential is in phase with the current. That can happen when there is only resistor, that is one possibility, or it can also happen when these two cancel each other. The voltage across the inductor is equal to the voltage across the capacitor, they cancel each other, then also we will have the phi is equal to 0. The phase shift can be adjusted to maximize the power output. Now we come to another important concept in this LRC circuit called the resonance. So note this word resonance. So we have the three elements connected in series. So we say RLC series circuit connected to a AC source. And I can write the current through the circuit, say the average value IRMS, as the total potential or the source voltage, which is applied to all these three, divided by the impedance of the circuit, impedance, Ohm's law. Voltage divided by impedance is equal to the current. For the impedance, I can write this in terms of the reactances and the resistance of these elements. What happens here, now we will change the frequency of the source. We know that XL is a function of the frequency, XC is also a function of frequency. So that tells you when you change the frequency of the AC source, the impedance will change, therefore the current will change. So it's a very nice thing happens when current is a small value, we have a small current. When the frequency is small, we have the small current, and it will increase, and at a certain value of frequency, it will become maximum, then it falls again. So we have a sharp peak like that. This phenomena is called, come to the front please, resonance. Move to the front please. Why do we call it resonance? This behavior, for a particular value of frequency, it peaks. When it is less than value, it drops. When you more than it also, when you change around this value, it becomes sharply, it drops to 0. At that particular value, it has a very high value. This is called resonance. The reason for that is because these impedances depends on the frequency. So that's why when the impedance changes, the current will change. So when the impedance is minimum, the current will be maximum. So we can get an expression for this resonance frequency. We call it resonance frequency. Where the resonance happens, that means when it peaks. When the current peaks, we at a certain value of the frequency of the source. So we call that frequency as the resonance frequency. We can get a formula expression for this resonance frequency by this logic. When does the resonance occur? Resonance occur when the current has its maximum value. When do you get the maximum value? Because the current is equal to delta V. We don't change the magnitude of the voltage. We only change the frequency of the source. When you change the frequency, XL and XC will change. That means the impedance will change. When the impedance is minimum, the current will be maximum, right? Because it's in the denominator. For a small value of Z, I will be maximum. R doesn't change with frequency, only thing that changes XL and XC. So what is the minimum value this quantity can become? What is the smallest value of XL minus XC? What is the smallest value this can take? It's a square, right? So it cannot be negative. So what is the smallest of the positive value? No, I mean 0. I mean, well, 0 is not positive, but the minimum this can be is 0. That can happen when this is 0. That means it can happen when reactive inductance is equal to the capacitive inductive reactance is equal to the capacitive reactance. We have the minimum Z value. So you know the formula for XL, this, for XC is this. We substitute and we do some algebra, then you get the expression for the resonance frequency. So now we know how we can get the resonance. The moment we make the frequency equal to this value for the given RLC circuit, it's a function of L and C, then that is where we get the resonance. So resonance has applications. Okay, theoretically, you know, this current can be, because what is current? Current is equal to delta V divided by the Z. Z is R squared plus this we made 0. When resonance happens, this is 0. So the current is delta V over R. Now, if R is 0, suppose the resistance is 0, with this, theoretically we can make it 0, we can imagine it is 0, but it never happens. Any wire you have will have some resistance. No matter how hard we try, there will be some resistance left. But theoretically, if R is 0, the current should become infinitely high, but that doesn't happen. Real circuits will always have some resistance. One application of this is the tuning a radio or TV station. So TV station, you know, you tune to a certain station, it has a certain frequency, like say 1000 hertz or 1 kilohertz or something. So this is the frequency of the radio station. So if your circuit, this LCR circuit or whatever LNC you have in a circuit, you can adjust the resonance frequency of that to match this frequency, then the current through the circuit will be maximum. So that means you are tuning into that particular radio station. And you know the equation is this. How can I adjust this to be the 1000 hertz? You can either change the L or change the capacitor. So normally what you do is to change the capacitor value. So for example, when you tune, you rotate the channel, you know, you move the, when you tune the radio, what you do is change the capacitance value. A varying capacitor, by adjusting its value, we can match it with the transmitting radio station and therefore catch the signal. So that is one application of this resonance frequency. Another one is metal detector. So, you know, in an airport, you have this metal detector. When you pass through it, it beeps. What happens there is the portal, let me call it the portal through which you are moving. It is, it's an inductor, okay? It has certain inductor coil or whatever, inductor. And the frequency for this inductor circuit is set to condition with no metal present. Okay, if suppose someone walk in with some metal pieces in his pocket, for example, it will change this inductor value. It will change this inductor value only with the metal. It doesn't happen with something else. If you carry a metal, because it will catch the magnetic field coming from this coil, so effectively it will change the inductor value. So if the inductor value before it was set to a certain inductor value, the moment you go through with the metal inside your pocket, it will change the inductance value of this portal. In turn, it will change the current that is going through it. It will be a very sharp change because of this resonance effect. And then the electronic will detect this change and it will beep the alarm. So that is how metal detectors work. So this is the last section, then I will finish. So, okay. Right, transformers. So I'll go a little faster. What is a transformer? Transformer is something that changes from one voltage to another voltage. Maybe you have the 210 volts, say in this side, 120. Let's say you want to. Okay, 210 is what you have. 220. I want to make it 110 volt. Step down. So we use coils. So this is the input, the primary coil. It will have certain number of turns. And there is a soft iron, so the whole magnetic field will be trapped inside this soft iron core. And here we have another coil, and the number of turns there is N2, different from N1. So now we can say that this voltage delta V1, and as the current flow, the voltage through the coil will also be delta V1, and it will be equal to, we will get it from the, what do you call, Lenz's law, or Faraday's law. The rate of change of flux through this coil multiplied by the number of turn will be equal to the source voltage, because it will just oppose it. There will be a back EMF which is trying to stop the current. So the potential difference between the coil will be equal to the same as the source, and it is given by flux change through the coil multiplied by N1. Now the same magnetic flux is going through the secondary coil also, the output. And by the same rule, we can say the delta V2 will be equal to, the flux is the same, right? It is trapped in the coil, the flux is the same. So delta V2 will be the same rate of change of flux multiplied by, but this time N2 there. So delta V1 is equal to this, delta V2 is equal to this. Let me go to the next slide. So I wrote this. That's what I wrote there. Now this is the same in both. That means combining these two equations, we get this. Delta V1 divided by N1 is equal to delta V2 divided by N2. So this is our transformer equation. What is the use of this transformer equation? Let me go to the last slide. This is the last slide. Now let me rewrite that equation. This is the voltage in the secondary coil. This is the voltage in the input, the primary coil. So by adjusting this ratio, if N2 is equal to N1, what happened? Secondary coil will have the same voltage as the primary coil. But suppose N2 is twice, say it is 200 and N1 is 100. Then the secondary coil voltage will be twice the primary coil voltage. So it's a transformer. It will, you can decrease also if I make it the other way around. N2 is 100 and N1 is 200, then you are half, making it half. So this is the principle of transformer. Right, so if N2 is greater than N1, then the transformer is referred to as step-up transformer because increase in the voltage. When this happens, N2 is less than N1, it is a step-down transformer. Right? Does it mean if you increase the voltage, does it mean we have got more power? No. I mean, we don't get something for nothing. The power is the same. So This is the power on the primary coil. This is the power on the secondary coil. If there are no power losses, there can be power losses due to heat and so on. If we ignore the power losses, then we can only say it is the same power on both coil. The output doesn't have bigger power. It will be the same power. So what happened? Delta VT is greater. It will make the current smaller. So the product must be the same. So we don't get something for nothing. So although the voltage increases, the current will decrease to keep the same product.